So hi everyone. Today's question is next greater element 1. Okay. So what the question basically is that you'll be given an array nums2 and you'll also be given an array nums1. So nums2 is basically like my input array. This is what my input is, and nums1 also given as an input, but this is like the query array. So we have to basically give the answer for all the queries in nums1, which are all the numbers in nums1. So what that answer is, I'll just be explaining right now. So basically for nums1, for all the elements in nums1, we have to find the next greater element in nums2. Okay. uh, what that basically means is, so for example, here in nums1 the first element is 4, right? So I'll find 4 in nums2, which is here, and then I'll look towards the right of 4 in nums2 and I'll try to find the closest greater element than 4. But as you can see here in nums2, there is no element towards the right of 4 that is greater than 4, right? So in such a case, we just return -1. Okay. Let's look at 1 now in nums1. So, so firstly, we find 1 in nums2, which is the first element. And then we look to the right of 1 and find the closest greater element, right? So that is 3 here. And then we return 3. Right? Similarly for 2, we do the same thing, and because 2 is the last element, so obviously there's no element towards the right, so obviously there's no greater element towards the right, so we just return -1. Okay, so for all the queries in nums1, we have to return this next greater element and make an output array, and what we finally have to return is this output array. Alright, so how do we solve this question? So there's a pretty easy solution for this, which is the algorithm that we just did right now, right? Which was basically going through every element in nums1, first finding it in nums2, and then looking towards the right of it one by one to find the next greater element, right? This algorithm takes big O of nums1 into nums2 time. So that's basically like big O of big O of length of nums1 into length of nums2 time, which will basically turn out to be big O of length of nums2 squared, right? Uh, but that so that's okay, but that's not the best we can do. The best we can do is better than that. So so how do we speed this up? How do we do this faster? So that's what I'm going to explain right now. So let's just shift to our whiteboard.
Okay, yeah. So yeah, this is the example that we have here, and nums2 is our entire array, and nums1 is the subset of nums2 for which we have to find the next greater elements, right? So for every element in nums1, I need to find the next greater element in nums2. So for 0, that element is just 6, because in nums2, the next greater element after 0 is 6, and for something like 2, it's also 6, because 0 is lesser than 2 and 6 is the next element that is greater than 2. So yeah, that's all. So how do we do this fast? Like we discussed how to do it like in a slow time complexity algorithm, but I want to do this fast, like specifically in linear time. So linear time for nums2. How will I be able to do that, right? So let's see. So it's actually a really interesting algorithm. What we're going to have here is that we're going to have a stack, right? And we're going to have a dictionary. So a dictionary is a hash map. I hope all of you know what that is. And what we're basically going to do is, in the dictionary, we're going to keep the keys as all the elements in nums2, and their values are going to be the next greater elements in nums2, right? So that will basically be our answer, right? If we have this dictionary, we can just read off the values of these elements in nums1 in the dictionary, and that'll be done. We'll have our answer. But how do we make this dictionary fast? So that's why we're going to use this stack, right? Now basically what we're going to do is we're going to start reading this array nums2 from left to right, and I'm just going to keep putting elements in my stack, right? But whenever I encounter a element that is greater than the current element at the top of the stack, I'm gonna pop off that element, right? And once I do that, I'm gonna set the value for that element that I just popped off as the value that was able to pop it off. So don't worry if you didn't understand. I think it's just better if we go into an example and you'll get it. So let's just start reading this the array nums2 from left to right. So first we have the number 3, right? Our stack is empty, so we just put in 3, right? Then we have the number 1. So 1 isn't greater than 3, so 1 is not able to pop 3 off. So we just write 1 in the stack also, right? We push 1 to the stack. And now we have 4, right? Now 4 is greater than 1, so 4 will be able to pop off 1, right? And once we pop off 1 from the stack, we have to write 1 and the value for that as 4 in our dictionary. So this is what I was saying, that the key is the element that just got popped off and the value is the element that was able to pop it off, right? So 4 was the element that popped. So 4 was the element that we're currently at. That is what popped off 1. So that's why the value is 4. Now we're still at 4, right? We haven't really added 4 to the stack yet. So the next element we encounter here is 3 at the top of the stack, right? But 4 is also bigger than 3. So it will also be able to pop off 3, right, from the stack. That means that 3 will also disappear, and we'll add this to our dictionary, that the value of 3 will become 4. Now the stack is empty, so we'll have to add 4 to the stack, right? The next element that we get is 2, right? So 2 is smaller than 4, so we just write 2 on the top and move on, right? So the next element we get is 0. Now 0 is smaller than 2, so we just write 0 in the stack and move on, right? And the next element is 6, right? Now 6 is greater than 0, right? So we pop off 0 and we add it to our dictionary like this, 0, and the value is the element that popped it off. So 6 was the element that popped 0 off, so that. Now 2 is also greater than 6. I'm so sorry. 6 is also greater than 2. So 2 also gets popped off, and the value of 2 is 6. And 4 is also lesser than 6. So 4 also gets popped off, and the value for that is 6 again, right? I'm just gonna increase my dictionary a bit. Yeah. And since this stack is empty now, so we just add 6 here. And now we have 5, right? So we moved on to 5, right? So we look at the top of the stack, and that's 6. So 6 is bigger than 5, so 5 can't pop off 6. So we just add 5 to the stack. And now we're done. We've passed through the entire array nums2. Once you've done this, if you're still left with some elements in your stack, just pop them off one by one and assign them the value -1. Okay. Now if you look closely, this dictionary exactly has what I said we wanted. So this dictionary has the keys, which are all the elements in nums2, and the values are all the next greater elements. So for 3, the next greater element was 4. For 2, the next greater element was 6. For 4, the next greater element was 6. And for 6 and 5, they didn't have any next greater elements, so we just write -1, right? So we've made our dictionary that we wanted. And now to make the answer array, it's just trivial, right? So what we do is, now we look at nums1 and we look at the first element, so it's 0. Now we read off the value of 0 in the hash map, and that's 6, so we just write 6 here. Similarly, we read off the value for 5, so that's -1, we just write -1. Read off the value for 2, so that's 6 again. we write 6, and the value for 1 is 4, so we write 4. And this is the answer, right? Because this dictionary had the next greater elements for all the elements in nums2, and we just had to read out the values after that. Yeah, so that's all. uh, the key part of this algorithm was creating this hash map using the stack, and how we use the stack to actually do that. Because whenever a larger element was encountered, only then we were popping off the smaller elements, and when we popped them off, we also stored this in a dictionary that this is the element that got popped off, and this was the element that popped it off. So because that was the element that popped it off, and only larger elements can pop off smaller elements, so we knew that this has to be the next greater element for that key, right? So yeah, that was the algorithm, and now I guess we can just move on to the implementation part.
So yeah, let's get started with the implementation. So I've just imported collections here because I'm going to use a DQ to model the stack. So let's just say stack is equal to collections dot DQ in blank. And we also need a dictionary, so I'm just going to call that D here. And after that, we need to go through all elements in nums2. And for each element, I need to compare it. For every element, I'll have to keep comparing it with the top of the stack, right? Till I reach an element, till either I reach the bottom of the stack, or till I reach an element in the top of the stack that is greater than that element, right? So I need a while loop here because I need to keep comparing it with every element at the top of the stack, even after I pop off the first element from the top. So I'm just going to say here while length of the stack is greater than equal to 0, right? And so we'll have two conditions. So if the length of the stack is 0, or the top of the stack has an element that is greater than my current element, then basically I just have to uh, add my element to the stack. So yeah, so we'll just push our element to the stack, and we'll break out of this inner while loop to go to the next element in nums2. So I'm sorry, this should be nums2, right? And so if this doesn't happen, then what we have to keep doing in the loop is, so I'll just write this explicitly here. So if the top element of the stack is lesser than my current element, then I have to keep popping it off, right? So I'll just pop this off and store it in an element called key. And then we have to write that the dictionary value of this key is equal to our current element, right? This is what we discussed in our algorithm. And yeah, that's basically it. So also I explained that after we go through all the elements in nums2, some elements might be left in the stack. So after this loop has completely executed, some elements might still be left in our stack. So for them, we just have to assign a value of -1, right? So I'll just write here while length of the stack is greater than 0, uh, stack dot, sorry, the dictionary key should be stack.pop, and the value for this key should be -1, right? So it will keep popping elements and assigning them the value -1. After this, I'm basically done. All I need to do is make an answer array in which I'm going to keep my answer, and then for every element in nums2, for every element in nums1, which is my kind of query array, I have to append its answer to the answer array, right? So the answer for every element would be just the value in the dictionary. So D of L. Yeah, that's all. And then we can just return answer, and let's try running this code. All right, so it runs on all the example test cases. Let's try submitting it. Okay, great. So the memory is pretty decent, and so is the runtime, right? Uh, so let's just explicitly discuss in big O what these runtimes and memories would be, right? So the memory would be big O of nums1 plus nums2, because The dictionary will take up a memory of big O of nums2, and this answer array that we create would take up a memory of big O of nums1, right? Um, in the worst case, in the best case, what we can have is that our memory usage can be big O of nums1, which is only using this answer array uh, as an extra space, which is what we were doing in our inefficient time algorithm that we discussed previously. Uh, yeah, so in this case, the memory isn't that much more. It's just big O of nums2. The entire memory can be modeled by that. The runtime is a little bit more complex to see. So the runtime, I'll just tell you the answer straight up. It's big O of nums2 plus nums1. So every element in nums2, this nested loop is going to work too. But the way to actually see this is that, so think about how many times we're actually going to touch every element in nums2, right? Uh, it's just going to be two times that we can touch every element in nums2. One is one is like while we're trying to append it to the stack, and one is when we're popping it off from the stack. These are the only times we're touching every element in nums2, right? This is so that would be two times nums2 for a time complexity basis, right? But as opposed to a traditional big O of nums2 squared algorithm, uh, what basically happens there is that we touch every element in the nums2 array nums2 number of times, right? Because for every element in nums2 array, I go through the whole nums2 array, and then for the next second element in the nums2 array, I go through the whole nums2 array again, and then for the third element in the nums2 array, I go through the whole nums2 array again. But that's not what we're doing here. In that case, we would have a big O of nums2 squared time complexity, right? Because in that case, we're going to be touching every element in nums2 number of times. That's how we get the big O of nums2 squared time complexity. But in our case, we're just touching every element in nums2 two times. That's why the time complexity for this loop and this also, or both of these combined, is big O of 2 times nums2, which is just big O of nums2. And the time complexity for this is big O of nums1. So the total time complexity is big O of nums2 plus nums1. And this can be compactly written as big O of nums2 because the length of nums1 is always going to be lesser than the length of nums2. So yeah, that's all. I hope you guys understood everything that I said, and I hope this video helped you. If you guys have any doubts, feel free to leave them in the comments. I'll definitely address them. And thank you. That's all.